Hello everyone. Today we are going to read the second part of our chapter 8, Force and Pressure. Pressure. You have learnt in class 7 that strong winds during a storm or a cyclone can blow away even the rooftops. You also learned that winds and cyclones are caused by the differences in air pressure. Is there any relation between pressure and force? Let us find out. Try to push a nail into a wooden plank by its head. Did you succeed? Try now to push the nail by the pointed end. Could you do it this time? Try cutting vegetables with a blunt knife and then with a sharp knife. Which is easier? Do you get the feeling that the area over which the force is applied, for example the pointed end of the nail, plays a role in making these tasks easier? The force acting on a unit area of surface is called pressure. Pressure is equal to force upon area on which it acts. At this stage, we consider only those forces which act perpendicular to the surface on which the pressure is to be computed. I now understand why porters place a round piece of cloth on their heads. When they have to carry heavy loads, by doing this, they increase the area of contact of the load with their head. So the pressure on their head is reduced and they find it easier to carry the load. Note that the area is in the denominator in the above expression. So the smaller the area, larger the pressure on a surface for the same force. The area of the pointed end of the nail is much smaller than that of its head. The same force therefore produces a pressure sufficient to push the pointed end of the nail into the wooden plank. Can you explain now why shoulder bags are provided with broad straps and not thin straps? And why the tools meant for cutting and piercing always have sharp edges? Do liquids and gases also exert pressure? Does it also depend on the area on which the force acts? Let us find out. Pressure exerted by liquids and gases. Take a transparent glass tube or a plastic pipe. The length of the pipe or tube should be about 25 cm and its diameter should be 5 to 7.5 cm. Also take a piece of thin sheet of a good quality rubber, say a rubber balloon. Stretch the rubber sheet tightly over one end of the pipe. Hold the pipe at the middle, keeping it in a vertical position. Ask one of your friends to pour some water in the pipe. Does the rubber sheet bulge out? Note also the height of the water column in the pipe. Pour some more water. Observe again the bulge in the rubber sheet and the height of the water column in the pipe. Repeat this process a few more times. Can you see any relation between the amount of the bulge in the rubber sheet and the height of the water column in the pipe? Activity 8.9. Take a plastic bottle. You can take a discarded water or soft drink bottle. Fix a cylindrical glass tube a few centimeters long near its bottom as shown in figure 8.15. You can do so by slightly heating one end of the glass tube and then quickly inserting it near the bottom of the bottle. Make sure that the water does not leak from the joint. If there is any leakage, seal it with molten wax. Cover the mouth of the glass tube with a thin rubber sheet as you did in activity 8.8. Now fill the bottle up to half with water. What do you observe? Why does the rubber sheet fixed to the glass tube bulge this time? Pour some more water in the bottle. Is there any change in the bulge of the rubber sheet? Note that the rubber sheet has been fixed on the side of the container and not at the bottom. Does the bulging of the rubber sheet in this case indicate that water exerts pressure on the sides of the container as well? Let us investigate further. Activity 8.10. Take an empty plastic bottle or a cylindrical container. You can take a used tin can or a used plastic bottle. Drill 4 holes all around near the bottom of the bottle. Make sure that the holes are at the same height from the bottom. Now fill the bottle with water. What do you observe? Do the different streams of water coming out of the holes fall at the same distance from the bottle? What does this indicate? Can you now say that liquids exert pressure on the walls of the container? Do gases also exert pressure? Do they also exert pressure on the walls of their containers? Let us find out. I have seen fountains of water coming out of the leaking joints or holes in pipes supplying water. Is it not due to the pressure exerted by water on the walls of the pipes? When you inflate a balloon, why do you have to close its mouth? What happens when you open the mouth of an inflated balloon? Suppose you have a balloon which has holes. Would you be able to inflate it? If not, why? Can we say that air exerts pressure in all directions? Do you recall what happens to the air in this bicycle tube when it has a puncture? Do these observations suggest that air exerts pressure on the inner walls of an inflated balloon or a tube? So we find that gases too exert pressure on the walls of their container. Atmospheric pressure. You know that there is air all around us. This envelope of air is known as the atmosphere. The atmospheric air extends up to many kilometers above the surface of the earth. The pressure exerted by this air is known as atmospheric pressure. We know that pressure is force per unit area. If we imagine a unit area and a very long cylinder standing on it filled with air, then the force of gravity on the air in this cylinder is the atmospheric pressure. But how large or small is the atmospheric pressure? Let us get an idea about its magnitude. Activity 8.11. Take a good quality rubber sucker. It looks like a small rubber cup, figure 8.18. Press it hard on a smooth plain surface. Does it stick to the surface? Now try to pull it off the surface. Can you do it? When you press the sucker, most of the air between its cup and the surface escapes out. The sucker sticks to the surface because the pressure of atmosphere acts on it. To pull the sucker off the surface, the applied force should be large enough to overcome the atmospheric pressure. This activity might give you an idea about the magnitude of atmospheric pressure. In fact, it would not be possible for any human being to pull the sucker off the surface if there were no air at all between the sucker and the surface. Does it give you an idea how large the atmospheric pressure is? If the area of my head were 15 cm into 15 cm, how much force air will exert on my head? The force due to air in a column of the height of the atmosphere and area 15 cm into 15 cm is nearly equal to the force of gravity on an object of mass 225 kg or 2250 Newton. The reason we are not crushed under this force of gravity is that the pressure inside our bodies is also equal to the atmospheric pressure and balances the pressure from outside. Did you know Otto von Guericke, a German scientist of the 17th century, invented a pump to extract air out of a vessel. With the help of this pump, he demonstrated dramatically the force of the air pressure. He joined two hollow metallic hemispheres of 51 cm diameter each and pumped air out of them. Then he employed 8 horses on each hemisphere to pull them apart. So great is the force of air pressure that the hemispheres could not be pulled apart. So this was the reading of our second part of chapter 8, Force and Pressure. If you have any doubt or query, you can ask me in the comment section below. Also, you can find the links to the other chapters and the playlist in the description box below. Thank you everyone.